So, we have seen plane waves in anisotropic medium, and it is very interesting to note that the electric field vectors experience two different refractive indices in an anisotropic medium, particularly in uniaxial medium. We have seen that the ray velocity and the wave velocity they are different. Under this heading, we will be discussing today that this index ellipsoid, the general representation of ellipsoid, which is the basis of understanding electromagnetic waves propagation in anisotropic medium. Then we will look at the ellipsoid matrix. We have seen the basic equation of ellipsoid while discussing this propagation in anisotropic medium. Then we will see that how this ellipsoid can be rotated through Euler angle rotation to find out the principal axis system. This will give rise to the transformation matrix. Then there will be another way of doing this transformation by matrix diagonalization. Then because it is a matrix, so we will end up with eigenvalues, eigenvectors, and incidentally we will see that it is very interesting that the two methods of Euler angle rotation and matrix method will give you the same result in terms of the eigenvalues and the transformation matrix or the eigenvectors. So, let us look at this index ellipsoid matrix, that is, in general, if you have an anisotropic medium which is characterized by the three refractive indices n x, n y and n z, you can write this index ellipsoid in this form. Note that this is the principal axis system, because you have three crystallographic axes along which the refractive indices are characterized as n x, n y and n z. But in any other coordinate system which is different from the crystallographic axis, crystallographic coordinate system, then this ellipsoid may look different. That is, you will have cross terms y z, z x, x y, and that is actually the general equation of an ellipsoid. And we will see that this ellipsoid is rotated from this ellipsoid when we consider with respect to the coordinate axis fixed with this system and fixed with any other system. So, when we consider the general ellipsoid equation, then it should it will look like this. You have an ellipsoid which is distorted, which is not distorted, which is having an inclination with the coordinate axis which is represented by the crystallographic axis, that is the principal axis system. So, in this system you can represent this x square by n x square plus y square by this. So, this is the ellipsoid equation, and this is also the general equation for the ellipsoid, and we considered that in general n x is not equal to n y, is not equal to n z. Now, it simply suggests that this ellipsoid and this ellipsoid are the same, but it is rotated, the axis is rotated or the ellipsoid is rotated with respect to the stationary axis system. Now, how we identify the ellipsoid? In other axis system, the ellipsoid is rotated from its principal axis system. That is what we have seen, that you have a coordinate system which is called the principal axis system, but in any other coordinate system this ellipsoid will be rotated. That is, if you rotate the coordinate system, then you can again coincide, you can again make the coordinate system and the ellipsoid coincide. So, you can identify this from the cross terms, that is y z, z x and x y. Cross terms signify rotations of the ellipsoid about the coordinate axis. The ellipsoid rotation, this kind of situation we will very often encounter in electro-optics and acousto-optics, and this is the basis of analyzing this electro-optic effect, acousto-optic effect, and also magneto-optic effects. That is, under some field the ellipsoid will be distorted, will be deformed, and then we will have to rotate, or we will have to give some transformation, so that we get back the principal axis system, and we can see that how the principal refractive indices have changed in the new coordinate system. So, that is the basis, and we will be mostly discussing our electro-optics and acousto-optics under the basis. That is why this discussion is very useful and very important. An electric field deforms the ellipsoid in general with a rotation or change in the length of the ellipsoid axis. So, we will also consider this situation. Changes in the, and this will be obvious in a situation of isotropic medium in electro-optic system, where there will be only change in the length of the ellipsoid, minor major axis length of the ellipsoid. So, changes in the squared term signify change in the ellipsoid axis, but in that case there is no rotation. Similar situation, all these things may also happen in the case of the presence of acoustic field. So, there may be a distortion of the ellipsoid in presence of the acoustic field, in presence of the electro-optic electric field, or in presence of the magnetic field, that also we will see later. Okay. So, ellipsoid under some field, you can see that this is the ellipsoid under some field. There has been only a change in the length when you compare this ellipsoid with this one, but the axes are the same, the principal axes are all the same, but there has been a change in the length of the minor and major axis of the ellipsoid. That is, you see p x square, q y square, and r square, because the new ellipsoid equation involves only the squared terms, x square, y square, and z square. As a result, there is no rotation, but if there are cross terms, that is x y, y z, z x, that means there is a rotation. So, we will understand this situation. Now, the means to transform this ellipsoid to the principal axis system, we consider that there are cross terms, that is, we consider that the ellipsoid is changed under the action of some electric field or acoustic field or magnetic field. We will understand this phenomenon. So, in that case one may apply this Euler angle rotations to make the axis coincide with the principal axis, but alternatively one can do that matrix diagonalization of the ellipsoid matrix to look for the principal axis system. The three principal refractive indices will be the result, and we will get the three eigenvalues from the diagonalization of the matrices, and we will also end up with three eigenvectors, which will give you the transformation for the new coordinate system, and we will see how it happens. So, in both the ways we will take an example, and we will use both the methods to see how the changed ellipsoid can be made coincident with the principal axis system. So, first we will consider, we have already seen that Euler angle rotation, but we will make a quick visit of this Euler angle rotation in order to make a comparison with the matrix diagonalization process. So, an ellipsoid for an isotropic medium, uniaxial medium under some field will look like this. So, this may be equal to some electro-optic coefficient multiplied by the electric field. We will see that situation, which can be put as a constant k. NO and NE, they are the ordinary and extraordinary refractive indices, and we are very familiar with this ellipsoid, which is for an uniaxial medium, but this is under the principal axis system, that is the crystallographic axis system. Now, corresponding to this equation, we can write the ellipsoid matrix as 1 by NO square, 1 by NO square by 1 by N. So, these are the diagonal elements of this. The k matrix, k elements will appear in this off diagonal positions. Now, this Euler angle rotation, while applying this, we will have to do some inspection, that because the cross term involves only x and y, therefore, it tells you that there should be a rotation along z, because it is independent of z, the cross terms are not involving any z. Then because it involves x and y, which is symmetric, if you change x by y or y by x, the equation does not change. That means, it implies that the rotation will be by 45 degree, and we have seen this in the earlier discussion also. So, a rotation about by 45 degree about the z axis will give you this transformation from this Euler angle rotation. If you write that matrix, so z prime will be equal to z, x will be represented in terms of this 45 degree of x and 45 degree of y, and similarly y prime will be represented. So, this is the transformed coordinate x dash, y dash and z dash, but we need the reverse transformation. So, knowing this, if we put the values of this, so from these two equations, x dash to x plus y, y dash to minus x plus y and z to z dash, we can actually write the reverse transformation in this form. So, the ellipsoid in the new coordinate system will look like this, because in place of x, if I substitute this value of this, so square of this will appear, square of this will appear in place of this equation, x square plus y square by n o square, z will remain z prime as it is. So, we will have a change in only the x square and y square. So, that is what we are trying to write. So, effectively we can write this, because you have 1 by n o square plus 1, so plus k. So, we put two of them in one bracket. So, this is the new coefficient which is attached to x dash square, and this should be equivalent to 1 by n x dash square, and this should be equivalent to, this should be equal to 1 by n y dash square, and z, this n e remains as it is. So, we started with a medium which was uniaxial, because x and y refractive indices were same, but now we get the refractive indices which are all of them are different for x, y and z. So, that represents a biaxial system. So, the new ellipsoid in this case we can write as n x dash square by n x prime square by this, y prime square by n y square, z prime square by n z square equal to. So, this is again the known form of the ellipsoid. So, that means, under Euler angle rotation we have been able to bring the ellipsoid back into the principal axis system, and we have used that n x square is equal to 1 upon n square plus k, and similarly n y square equal to. So, let us remember that n x dash, the new n x representation for the principal axis system is equal to this, and n y for the new principal axis system will be equal to this, and n z equal to this. So, these are the three values of this n x, n y and n z. We will see the same result when we will apply this diagonalization method. Also remember that this transformation we imposed, that is x dash equal to this, y dash equal to this, which is corresponding to this matrix. This will correspond to this matrix, because this will give you 1 by root 2, this will be 1 by root 2, this will be minus 1 by root 2, and z for this will be equal to 0. So, this is the transformation matrix from x dash y dash z dash to from x y z to x dash y dash z dash. But we need the reverse transformation, that is, we have to express this x y z in terms of x prime, y prime and z prime. So, then the matrix will look like this, x y z will become 1 by root 2 minus 1, because in that case we will use this relation. So, these are the transformation matrix from x to x dash frame, whereas this is the transformation matrix which is from x dash frame to x frame. But we have used this. So, this equation we will remember and we will compare with the result that we obtain from the method of diagonalization. Okay. Now, we will use this matrix diagonalization. This will yield 3 principal refractive indices as eigenvalues. These 3 eigenvectors will be used to devise the new coordinate system, which will correspond to the transformation, and this will give you the new principal axis system. So, this is the mathematical operation that we will perform with this ellipsoid matrix, index ellipsoid matrix. So, this matrix we just write for 1 by n o square equal to a, 1 by n o square equal to a, and 1 by n e square equal to b. Therefore, this matrix equation for diagonalization, we have to write this eigenvalue equation, which is equal to determinant of this matrix A minus lambda I equal to, which is the eigenvalue matrix, is equal to 0, which is again very well known in the basic mathematics of matrix diagonalization. And by doing so, we write this determinant of this equal to 0, because a minus lambda, b minus lambda, this determinant will be equal to 0. If you open up the bracket, we will get this a minus lambda, b minus lambda, and k square b minus lambda equal to 0. Just from here, k this into this. Okay. So, from this equation, if you take b minus lambda bracketed out, then you will have a minus lambda square minus k square equal to 0. This gives you 2 possibilities, that this bracket may correspond to equal to 0, or this bracket b minus lambda may correspond to equal to 0. So, the eigenvalues are corresponding to this bracket will be equal to a plus k lambda, and the other value will be a minus k, which is obvious from here, a minus lambda equal to plus minus k. So, these are the 2 roots of the that results from the first bracket, and lambda equal to b, it comes from this bracket, b equal to lambda. Therefore, we get the eigenvalues, because lambda equal to a, lambda, because we have substituted a equal to 1 by n o square and b equal to 1 by n e square. If we get it back, then we can write this, the eigenvalues lambda equal to 1 by n o square plus k, this will be 1 by n o square minus k, which are exactly the same that we obtained from the Euler angle rotation. So, this is your new n x square, 1 upon n x square, and this is 1 upon 1 n y square, which is the new principal refractive indices. This 1 by n z square, n e square, that remains the same. Now, we will have to look for the eigenvectors. Recall that eigenvalue equation A x equal to lambda x, and the eigenvector corresponding to this lambda a plus k, which is the first eigenvector we have called a plus k. If I use this eigenvector, then we can write this equation as a x equal to the eigenvalue a plus k x. So, if I just take the 3 simultaneous equation obtained from this matrix equation, a x plus k y equal to a x plus k x, this simply says that if you remove a x from either side, then you will end up with k y equal to k x. That means, x must be equal to y. So, that is what is implied by writing x equal to y. From the second equation, a y and a y will cancel from either side. which will give you k x equal to k y, and that yields the same equation, that is the same relation, that is x is equal to y. But from the third equation b z equal to a plus k into z. So, it tells you that because a plus k cannot be equal to b. So, therefore, b z must be equal to 0. Therefore, you get the eigenvector x equal to x, y and z, because x equal to y. So, putting x equal to y equal to c, we can write that 1 1 0, c if you take outside. Now, since x square plus y square plus z square equal to 1, then you can write this normalized eigenvector 1 by root 2 1 1 0. And in the same way, we will consider the second eigenvalue, that is lambda equal to a minus k. We will substitute in the eigenvalue equation a b x y z, the eigenvalue and again the eigenvector. Therefore, we again get the three equations, simultaneous equations, and these are a x plus k y equal to, you can remove a x from either side, that tells you that k y equal to minus k x, which is very straightforward, that minus x equal to y, and from the second equation if you remove a y, you get k x equal to minus k y, that also gives you the same relation, that is k x equal to minus y. Now, if y equal to c, then x will become equal to minus c, and if you put it back, the third one also gives you that z is equal to 0. In the same way, we found in the first eigenvalue case, that is b and a minus k, they are very unlikely to be equal. In that case, z must be equal to 0. So, we get this eigenvector corresponding to the eigenvalue a minus k. Let us now see the third eigenvalue, that is corresponding to lambda equal to b. We have this eigenvalue equation in this case, this is the eigenvalue and this is the eigenvector. The three simultaneous equations are this. So, from the first equation a x plus k y equal to b x, what does it mean? It means that y equal to b minus a by k into x. From the second equation, we get k x plus a y equal to b y. This means x is equal to b minus a by k into y, which are very difficult, I mean which will give you this equation b minus k equal to k by b minus a. So, that gives you b minus a square equal to k square. Therefore, you will have, which is indeed very difficult to give one unique value of x and y. B will be equal to a plus k or b is equal to a minus k. So, both the possibilities, the connection with a and b are including both the values a plus k or a minus k, but eigen values must be distinct and they should not merge, they should be separate. So, as a result, this x, this cannot give you any solution. So, therefore, x equal to 0 and y is also equal to 0, and z will have a free choice, because on either side b z equal to b z. So, that means you can take z can assume any value. So, you have a free choice of z. If I use this relation that x equal to 0, y equal to 0 and z equal to c, then we can write that eigenvector x equal to c 0 0 1, and under normalization we can write this equation like 0 0 1. Now, we have 3 eigenvalues and 3 eigenvectors. Then if I combine these 3 eigenvectors, then we can write this equation, this matrix as 1 by root 2 minus 1 by root 2. You can see this from here, 1 upon root 2, 1 upon root 2 0, here 1 upon minus 1 upon root 2 plus 1 upon root 2 0, and this will be 0 0 1. So, I just combine all 3 eigenvectors together, which is nothing but the transformation matrix that we obtained from the Euler angle rotation. So, we have discussed in this context that a general index ellipsoid, which is very useful in analyzing the waves, electromagnetic waves in anisotropic medium, and how this ellipsoid will look in general coordinate system, which is different from the principal axis system. This ellipsoid will associate itself with an ellipsoid matrix. So, there are means of bringing the ellipsoid, which is otherwise not looking very simple, to bring it back to the principal axis system. There are methods. One is this Euler angle rotation, that if I can give the proper rotation to the coordinate axis, then we can make the coordinate axis coincide with the principal axis system, that is the one which are associated with the crystallographic axis. The other method is to use this matrix transformation, and by diagonalizing the matrices we can and again get the eigenvalues and eigenvectors. We have seen that by using Euler angle rotation we get the principal refractive indices, and we also find the transformation matrix. By matrix diagonalization we also found that the three principal refractive indices, which are the same as we obtained from here, and these three eigenvectors were combined together to get the transformation matrix. So, this discussion is very useful and we will be very often on using in the analysis of electro-optic effect, the modulators, switching of the modulators by considering just diagonalization or this Euler angle inspection for evaluating the electro-optic, magneto-optic and acousto-optic effects. Thank you very much.